We haven't talked about the tangent function yet. Now this is the third trigonometric function. We have sine and we have cosine. Tangents is a little different than sine and cosine. Notice they're quite, sine and cosine are quite similar in terms of their graphs and stuff like that. Tan is different. So I'm going to define tan for you in an easy way. To find the tan of an angle, you can just take sine and take cos, and you're looking for the ratio of them. So it's actually the ratio of ratios of sides of a triangle. But if you think about it, the ratio of sides is still just a ratio of sides. So there must still be a way to extrapolate it from the 90-degree definition. In fact, sine is, opposite over hypotenuse, and we know that cosine is opposite over hypotenuse. Because the denominator is the same, we can pretty much get rid of it, and we actually have over a. So another way of thinking about the tan of an angle is that it's just the opposite over the adjacent. But a lot of people prefer this definition, especially when you move to higher level of mathematics. It comes up a lot. So that's what I'm going to define it as. That's what I want you to remember it as. But also realize that you can actually talk about being the opposite over the adjacent. So if we draw that now infamous triangle that we had before, this, is 30 degrees in this case. We know the tan of 30 degrees. Oops, I've got it the wrong way around. There we go. Tan of 30 degrees must be 1 divided by root 3, right? Similarly, tan of 60 degrees, again, so opposite over adjacent, it's going to be root 3 over 1, right? So the corresponding table, you could add tan to the table row I had before. But if we just think about these values, 0, 30, 45, 60, and 90, I should have still kept that other table for this video. But tan of 0, because sine of 0 was 0, tan of 0 is 0, right? So remember, tan is sine over cos. So because sine of 0 is 0, it's 0 divided by something, it doesn't matter. Tan is going to be 0. Now, 30 degrees, if you remember, sine and cos were actually, so sine of 30 is a half, and cos of 30 was root 3 over 2. And if I do that division, I get 1 over root 3, right? Or I could just use the work we did up here. This is, 1 over root 3. Similarly, over here it was root 3. And then at 45, remember in a isosceles triangle, the sine and cosine were the same, so this is just going to be 1 actually. So two things divided by each other, if they have the same value, it's 1. For example, like 5 over 5 is equal to 1, right? So what's tan of 90 degrees? Well, it's a bit tricky to work out actually, because if you remember what the table looked like there, we had sine of 90 was 0, and cos of 90 was equal to, or sorry, sine of 90 was 1 and cos of 90 was equal to 0. So tan of 90 should be then 1 divided by 0. But you can't divide by 0 in maths. That's bad. So this doesn't really make any sense. So what is tan of 90? Actually, it's undefined. There is no such thing as tan of 90. And that's okay. Sometimes functions in mathematics, you can't define them. So maybe you haven't met this before, but basically, there is no value at that point. So if I tried to sketch a graph of tan, but what I can say is that if you think about what it looks like near that point, so if we draw in 90 degrees here, so there can be no value at 90 degrees for tan. We know that tan is 0, 0. They actually work out, it must do something like this, right? Because, so why would that be the case? So sine of 89.9 is, something really close to 1. And cos of 89.9 is something really close to 0. Now, if I divide by a number that's really tiny, I'm basically asking myself, how many times does this really tiny number go into something that's pretty much 1? And the answer gets big really quickly. Okay, so imagine you try to divide 1 by, 0.00001. Let's say that. I think the answer in this case is 100,000 times, right? So that's how many times the division thing goes in. So that's a huge number. So basically, this will shoot off to infinity, but not quite get there, leaving you with this kind of graph shape here. And then if we go to the other direction, notice that cos goes negative after we breach that 90 point. So cos of 90.0 or something like 90.01, right? This would be now a negative tiny number. And we end up coming down here. And then we do this kind of thing. And we end up going back up. So you can verify that for yourself. But tan will do that. That's the graph of tan. And it will repeat in this fashion. So notice the period of tan only has a 180 degree period. This is minus 90 degrees. It's 270 degrees. So there's asymptotes at 180 degree intervals, right? And they're spaced out like that. So that's the period of the graph. That's the section of the graph that we're interested in. That's tan, right? Tan comes up a lot as we move forward. Make sure you know how to sketch this graph as well, just off by heart. We're going to use it in many different settings. Right, what's next? So those are 3 of the 6 basic trigonometric functions. So I'll just introduce 3 more. I'll just write down what they are. We have sec, we have cosec, and we have cotan. Now each of these 3 functions I can actually just get by looking at the third letter. Sec is defined as 1 divided by cos, right? Cosec is defined as 1 divided by sine. Cotan is defined as 1 divided by tan. Okay, so what do the graphs of these functions look like? Well, if I take the cos graph, I can get the graph of sec just by looking at the graph of cos. Okay, the way I want to deal with that is that I'll just do a quick sketch of the graph of cos here. So it does like that. Now how could I get sec from this? Well, basically, at this point, that's bad, and at this point, that's bad, so I can't really divide by 0 there. So the corresponding graph of sec, again, will have asymptotes at that point, right? It might suggest similarities to tan function. Again, that's actually to do with a Pythagorean identity that we're going to talk about in a later video, but here, okay, 1 divided by 1 is just 1. As I get, closer and closer to that singularity there, I must do something like this. And then I'll have this kind of fashion here. And then like that. So the graph of sec will just look like all those waves that we had, sort of like they end up like this. Just happy faces and sad faces all over the place. That's what we're dealing with, right? And sine similar. So I'm just not going to sketch cosec. It's just almost exactly the same. And then to get cotan, it's similar again. You just kind of want to do the reciprocal of this graph. It's a bit harder maybe to think about it first because we have singularities where the tan is. But that doesn't bother us too much, really. If we think about dividing by 0, all the singularities now in the cut graph are going to be shifted to where the zeros are of the tan graph. So if I was to sketch cut, I'd have singularities at 0, 180, 360, and so on. What happens near the points where I'm dividing by a really big number? If I'm dividing by a really big number, I'm pretty much going to get 0. Okay, and in fact, you can easily just sketch the graph of cos from those sort of informal observations. So just by kind of thinking about functions like that, you see the cos must look a bit like this, with asymptote at 180, and so on, right? Again, there's an asymptote at the origin as well. So that's cot. So that's the graph of cot. So those functions you won't see again for a little bit in this course, but I'm just sort of introducing them now so that when you do see them, you know how to sketch them and you know how to, what they're referring to. They're just 1 divided by each of the 3 we introduced, and those are the names, and we can tell that from the third letter. That's the trick, right? If the names seem a bit out there, you can just look at the third letter and then you know which one you're referring to.